So we're calling it consequential LCA approaches to transportation energy policy. Here we're really talking about passenger cars, and we're talking about two case studies that Dr. Katie Whitefit did for her dissertation. And this is going to be an example of nuts and bolts. So if you're interested in sort of constructing this kind of model that really integrates LCA and economics, far beyond the simple examples that we looked at in class up to now. What today is trying to do by presenting Katie's work is to really give you an appreciation of what that takes. And I think some of you are going to check out on some of the details here, and I'm trying to present it as high of a level as I can while still being substantive. But hopefully what's going to come out is the benefit of being tenacious with this kind of a problem. The kinds of analyses that Katie was able to pull off in her dissertation are very important and very needed. And we look at policy intersection with the desire for companies to make profit and consumers to have their preferences satisfied. Pulling all that together in a single framework, it's obviously multidisciplinary, but it is also, it's 1 to 2 years of work. So to give you a sense of what that's all about, let's start at the beginning. We discussed what LCA is, and we talked about good LCA data and bad LCA data, and we talked about protocol there, and we tried to be really clear about what you can use an LCA for and what you can't use an LCA for. You can use an LCA for the study of something that exists, that if it's being used in a design context, as long as that design is not radically different from things that already exist, you can use literature data to infer what you might see going forward. We use the example of the aluminum-intensive vehicle. The idea that if we lightweight the vehicle, that's great in the use phase, but there are some additional production burdens. So you want to think about the trade-off there and how long it takes for the emissions you invest in the production stage to actually be made up for in the use phase by higher fuel economy. And LCA is great at telling us, maybe it's going to be about 3 years if your aluminum comes from North America, but we talked about geographical context, and we talked about how even in different temporal contexts, maybe your answer is going to change. And even today, just looking at aluminum that might be sourced, a typical kilogram that might come from China, that payback period might be a lot longer. So these are important studies in and of themselves. When we start talking about sustainability, as opposed to a life cycle assessment, they're broader questions, and we went through these questions before. Would people buy such a car? Would producers have an incentive to make such a car? And if there was an alignment of those incentives, where would the aluminum come from? So now you get companies like Alcoa that are going to be meeting a new demand. They might get aluminum from new places. The price of aluminum might be affected. The price of aluminum might go up. People then might not be very interested in these vehicles after the price goes up, and ultimately, that aluminum-intensive vehicle approach may not have been such a good idea after all. And ultimately, maybe this isn't about aluminum-intensive vehicles, and maybe government doesn't want to be in the business of regulating design specifically, but maybe thinking more broadly about how to nudge the system to go in a direction that might be more favorable from a carbon perspective. So when we go from life cycle assessment to consequential life cycle assessment, we're now thinking about, okay, well, we're going to perturb the system with a new type of technology. How's that technology, or how's that market going to respond to the technology? How much of it's going to be uptaken, and what are the ultimate benefits going to be? That led us to this cartoon drawing that's come up a few times this semester. Thinking about the life cycle emissions as consequences of the market. So you've got the supply side, you've got the demand side, both of them thinking about available technologies. Government can incentivize technology, it can incentivize research, it can tax or subsidize companies and consumers. So there are a lot of levers that are at play in the system, and ultimately, if we're thinking about an example of passenger vehicles and the desire to get the carbon emissions down significantly, the space here to act in is very large. And how do we sort of move beyond the food fight that exists? You've got producers saying that every cost-efficient technology has been put on the vehicles already, so there's nothing more we can do. Or the argument you hear more often these days, which is, well, consumers will never go for it. Or the other side of this, you've got environmentalists saying that this is an imperative, and company profits be damned, right? So these are extremes of the argument, and rational people are somewhere in between. But the point is, how do you sift through this system in a sort of quantitative way, the kind of way that engineers might be used to attacking a problem? So that's where we're going, and we're presenting the work in this direction that Katie did, and I'm basically expressing this in the way she expressed it. I think she did a really nice job. And what I'm going to do is just sort of keep this as high a level as I can, and I'm going to mention where appropriate that there's going from this slide to this slide is about a year of work, and it's not trivial kind of thing. So we'll talk about sort of the disciplines involved as we go through. So starting at the top, and you can follow along with a nice key up here at the top with an introduction. So we already know environmental impact, external to the market, generally a negative externality. We don't have an alignment between the social cost and private cost, and we've seen that already this term talking about it. And generally where you don't have this intervention of regulation into the market, you end up with total costs that are actually higher than the minimum that's possible. And that's where policies come in. But the question is, how do you design policy, especially in a complex system such as the passenger vehicle market? So we're beginning to see now in the last, if we take the U.S. fuel economy regulations out, we start looking at the more progressive regulations here, really in the last 10 years. Government sort of creating incentives and let's call them carrots and sticks to basically affect the design of products directly. So we're going to ban incandescent light bulbs, for instance. The fuel economy regulations have been at play for a while, but even the reformed CAFE standards that are kicking into effect now have a footprint basis. Basically, they're normalized to the size of the vehicle, and there's a design implication there, right? Appliance efficiency standards. We've talked about the Energy Using Products Directive. We've talked about the recycling directives in Europe. Similar things going on in Japan. These days, we're seeing subsidies for electric vehicles, right? So government's realizing that, especially in austere times, the ounce of prevention is worth the pound of cure, and therefore, let's see if we can influence the design stage. And that's obviously a tricky business. So the question to ask is, if government is going to be involved in the design of products through regulation, where's the methodology? Where's the class you take that teaches you how to do this or teaches them how to do this? And the point here is that it really doesn't exist. And the answer to this question, can a policy induce a desired design change? Of course it can. But what's the systematic methodology to know whether you've got the right policy? And what other, perhaps unintended consequences may arise from the implementation of that policy? We need methods, right? So it is somewhat self-evident, and certainly we've discussed this enough times now, that if you're going to answer these two questions, you need to understand the interaction between the demand, the engineering trade-offs, and the constraints that are just driven by physics, and the economic structure of the industry and the costs of technology. And there's existing literature in engineering, there's literature in economics that are beginning to move in this direction, and even in life cycle assessment, moving in this direction. But they're sort of converging on a target, but I would make an argument before Katie's thesis, it really hadn't happened. So what's outlined here in this presentation is just a high-level overview of what's going on in the disciplines that are making contributions to this problem. What is the methodology, the sort of structure of the methodology, and then a few more details on the engineering model and the demand model. And between the engineering model and the demand model, this was about 2.5 years of time. Okay, so I'll just, it'll look like 4 or 5 slides to you, but it is not trivial at all. And then get to the interesting part, looking at 2 case studies, one on the reformed CAFE standards and the other on, both are on the CAFE standards, but one's looking at a prediction of how effective it might be and how that 2012 CAFE standard might affect domestic automakers versus foreign automakers. And the second case study then is looking at whether cars might get bigger because of the CAFE study or CAFE policy. Okay, so we'll get to that, and probably we'll spill over into the next time a bit. Okay, big picture, seem to make sense what we're trying to do here. You're not going to walk out of this being able to do it, but we've made the argument enough times. We need to understand the environmental system. We've done a pretty good job of that. We need to understand the life cycle. We've done a pretty good job of that. The idea that economics is important. We've done a pretty good job of that, but we haven't, sort of tackled big real-world problems. And the idea here is that we can do it. It's hard, and hopefully at least a few of you would be interested in thinking about that down the road. Okay, so I've covered these 3 areas already. Talking about the literature, so I mentioned the 3 areas already: engineering, economics, and life cycle assessment. Beginning with engineering, there has been a few pieces of work recognizing how policy and economic structure come together. And Professor Jeremy Mihalik is a graduate of 589. Back in 2002, I think he took the course, and it was his class project that actually led to about 3 PhD dissertations down the road, including Katie's. So, and I won't talk about what his term project was because it might intimidate people. It was he really got into it. But it actually opened the gateways to actually do real-world problems. He looked at a simplified market and simplified demand models, but he actually showed that you could bring these areas together. His student at CMU is Norman Shao, and he's done some work there. There are also 2 other students that got their doctorate looking at work bringing engineering and economics together. But in the case of Paniotis and Bart here, they weren't looking at the policy side, just bringing the economic models together with the engineering models. When you think about the math of it, and you're trying to optimize systems, right? You're trying to achieve environmental objectives at minimum cost. This becomes about optimization. So beneath the surface here, you don't just stick fancy models into Excel. I mean, you already had bad experiences with the solver already with simple models, right? So actually figuring out how to get solutions to these problems, it's non-trivial. So thinking about optimal design when you bring economics and engineering together, has been some work in that area. But you can get a sense that this has not been, widely pursued and universally pursued. I mean, this is an area that's actually new. So I call it market-driven design is the field, and there's less than a dozen very active researchers in that field. Okay, in all this work, we're referring to the representations of demand and the representations of competition are simplified. So when we talk about contributions here, these are Katie's contributions and what some of the work we're going to present here. Looking at real demand models and bringing real demand models in with design optimization. And a full-scale model. So we're going to be talking about 500 vehicles that are being studied as they respond to CAFE standards and 20 different firms. So very large scale problem, and doing optimization, even for these small problems, is tricky. Now, think about it at a larger scale. So there's a lot going on there. The economists are beginning to figure out that thinking about design is important. And if you look at what's going on in the industrial economics literature, generally design is fixed. So if I'm studying a CAFE standard, you're not going to look at the possibility that GM or Ford has to maybe change the size of an engine to respond to the CAFE standard, tune it differently with different gearing. Basically, they're going to look at design as being fixed and then figure out what price changes that these companies would need to make. So I will make my more fuel-efficient vehicles less expensive, so more people buy them. And I'll make my more fuel-inefficient vehicles, or gas guzzlers, I'm going to make them more expensive. And that way I'm going to meet the corporate average fuel economy target, the CAFE target. So now that's what would happen if your design is fixed. But you might imagine that that would be pretty expensive, right? Maybe I still want to make the gas guzzler maybe a little less gas guzzling by just tuning some parameters. Maybe it's a shift logic or just using different lubricants. And that may not be expensive at all. So clearly design isn't fixed. If you treat design as fixed, you're going to have higher costs than the companies actually would see under a real CAFE standard. But you can begin to imagine, if you don't have the people who are doing the economic studies talking to the people who understand the engineering design, good luck making those connections, right? And that's one of the big reasons that it hadn't happened. Now, in very recent work here, you're beginning to see, a few economists recognizing that, if I just look at the short term, if I put a policy on the industry this year, maybe they only can respond with price changes. In the very long term, everything can change, right? So looking 20 years out, the companies are completely flexible, right? I mean, subject to market forces and profit, of course, but there's this in-between zone where usually CAFE standard's going to happen. You've got maybe 3 to 7 years as a company to actually respond to that. Some things are fixed, other things are not fixed. So we call that the medium term. And these researchers here have been thinking about the medium term. They realize that if I just do a long-term analysis, I'm going to have costs that are too low. I'm going to figure out that the CAFE is actually a lot easier to or less costly to apply than it really is. If I just look in the very short term, it's going to be too expensive. The reality is in the middle. So you need to look in the medium term. You need to consider design. But what the economists did, these folks, is look in the literature for design trade-offs. So you can basically look at vehicles on the market this year, last year, or the year before, and get a sense of what the market has expressed with respect to trade-offs of fuel economy and acceleration and price. And that's good. It gets you in the right direction, but that's not going to be particularly helpful when you've got a big change in the market. So if I go from 26.5 miles per gallon, and it's been flat there for 15 years, now I go up to 35 miles per gallon, maybe even up to 55 miles per gallon, as you might have read in the news. Well, new technologies that have not been expressed in the market previously are going to be considered by these companies. So basically, you're going to have a hard time using the past to predict the future, right? So what Katie has done here by way of contributions is bringing engineering design models into the market analysis, and thereby being able to not only predict the performance of a vehicle that might have a future technology on it, but by integrating that with the economic framework, then whether that might be a profitable vehicle, she can figure that out. Okay, so where the line gets drawn is economists can look at what exists in the market if they're going to consider design, But if the market's going to change a lot, new designs may come out that they would have no way of predicting. So what you do, and what Katie has done, is she's looked at up to 256 combinations of technologies that are not typically found on vehicles. They are found on some. And basically, to respond to CAFE, producers can change the engine size, and they can change the gearing, and they can slap on cost-effective combinations of new technology. So these would be responses that you'd really have no way of capturing any other way than being able to model the engineering here. Okay, and then I'll talk about it in a minute, how that gets integrated with the demand side. Is this clear so far? High level? What's going on? Is this sounding hard yet, or not yet? It sounds pretty easy up to here. The other thing you might be thinking is, what we're talking about here seems kind of obvious, right? And maybe more than one of you is a little frightened that this stuff hasn't really been going on the whole time. You just kind of assume that there's so much money involved, and the greenhouse gas issue is so important that they've nailed how to do these assessments. And and I don't want to say flying blind, because there have been a lot of studies, but I think what we're making a case here is integrating the engineering into the economics is a pretty important thing, and really that has not been done in the kind of way that I think most of us would be comfortable with. So thinking about energy efficiency, now this is a bit more general, moving outside the world of cars. Typically we think about the idea of cost effectiveness. So when EPA is considering applying a new regulation, they have to talk about, okay, well, what are the increased costs and what are the benefits to the consumer? And usually that cost-benefit analysis is as far as the whole thing goes. What Katie is pointing out here is that there may be other benefits or other opportunities that companies have to affect the design that don't really show up obviously as increased in costs or reduced, say, fuel consumption in the use phase or reduced electricity consumption in the use phase. So, for instance, I may take a combination of technologies that gives me both higher fuel economy and higher acceleration. And I can basically tune that combination of technologies in a way where maybe I'm not giving all the benefit to fuel economy. I'm giving some of the benefit to fuel economy, but I'm also giving a benefit to acceleration because people like that too, right? Or I think about a technology like lightweighting that can basically improve both fuel economy and acceleration, right? The story, the whole sort of energy efficiency field is consumed with cost-benefit analysis. But the reality is in the market, it's not just about the cost of the technology and then the benefit of the energy savings. It is about the value in totality that product is providing, and being able to understand how firms might respond, not just with respect to fuel economy, but say in this case in cars with acceleration. That's going to be very important. All right. So to give you an extreme example, let's suppose fuel prices are really cheap, and it's very expensive to improve fuel economy, and which it isn't, but let's just suppose it were. And now the government says, well, 50 miles per gallon next year. What do you think is going to happen? Well, people are going to say, all right, if I'm buying a new car this year, it's going to have this really high, fuel economy rating, but gas is cheap, and I'm paying a lot for that, right? And it not bringing a lot of value to me, so I'm going to hang on to my car, right? So the point is, under that circumstance, maybe the producer, who wants to desperately sell cars, they're going to start packing other features in that car, right? It's kind of an obvious thing. But the analyses as they have been done, haven't captured other attributes. So the key that Katie's bringing to the table here is capturing trade-offs between energy efficiency and cost, as well as these other attributes. Okay, is that making sense? Good. Yes. Yes. It's both sides, right? So if you have a cost that is borne by the supplier, because ultimately the supplier is buying the materials and doing the manufacturing, they are not willing to eat that, right? So it's going to show up, straight away in the market. Ultimately, the source of the money is the consumers. So the consumers pay in the end. But where producers pay is in losses of profit, right? And we can get into the complexities of this. There are certain quarters where companies lose money, they don't gain money. So even with what we're going to present here, we're far from a perfect state. We're just going to consider a single period here. But the point is they both pay, and profits are affected by the number of players in the market, number of vehicles in the market, and depending on the regulation and the attitude of consumers toward willingness to pay for certain attributes, those profits may go up and down. The consumers are going to pay for sure in the use phase, right? So they're buying the consumables. So it's a system thing, and you can't, and the message I'm trying to send here is it's hard to pull it apart. So I think that's an excellent question, because EPA thinks about it, it's this camp and that camp. So what is the impact on producers? What's the impact on consumers? But really, this is a complex system. Other questions? You're starting to get a feel for the state of the art. A life cycle assessment we've talked a lot about, so no need to say any more about what life cycle assessment is. What I may not have mentioned when we talked about consequential LCA was that the studies that are out there don't deal with competitive market systems. Well, no, I said that wrong. Market systems that are not subject to perfect competition. So generally what we're talking about here are commodities. So a good example is, I'm going to look at fish stocks, right? So salmon is salmon, right? Unless you try to sell, Alaskan salmon or, you can get into that. But the point is that, if I want to look at maybe it's Atlantic salmon, and, so I've got a bunch of boats out there fishing these salmon, and, if I've got too many boats, then the stocks are going to deplete. As those stocks deplete, then I may be more enticed to look for other fish. So if I'm interested in how fishing of salmon affects cod, I don't know fish, but fish has come up far too many times this term for me to know nothing about fish. But the point is how one commodity might affect another. Okay, that's different from you're not designing the salmon. You're only making a decision about the quantity that's being fished in that case, right? So there's been work done in that area. There's been some work done on ethanol, right? Ethanol is ethanol, it's a commodity. But you can say, well, where did it come from, corn or sugar? In these cases, just looking at a single situation there. But they're not designed products, okay? So what Katie has done is sort of brought consequential LCA into the product sphere, competitive products, not the commodity product. And then the integrated model then looks a lot like our cartoon. It's just drawn a little bit differently. So on the demand side, what's input is basically an understanding of consumers. So anybody taken the new car survey? You buy a new car and you get something in the mail. It's a survey, and then you fill it out and you mail it back. Anybody heard of the new car survey? Yeah, I got one or two back there. So yeah, so taking that data, part of that is demographics And part of that is, okay, what's the first choice, the second choice, the third choice? You know, if I didn't buy this car, I might have bought this car. If I didn't buy that car, I might have bought a third car. So what data inputs to the demand model? So that's what's going on here. On the supply side, there's two things. One is that engineering design model. And the second is my model of competition. So we're going to assume here that this system is acting in equilibrium, meaning that prices are being set and designs are being set such that no producer has an incentive to change their design or change their prices. If they did, they would lose money. And that idea is called economic equilibrium. You can probably take 2 classes or more just studying economic equilibrium. And the point of economic equilibrium is that you might say, well, you know, the automotive market is dynamic and no way that can be an equilibrium. But there have been studies to show that, including some that we've done, that equilibrium is actually a decent model, even though the intuitive notion of what economic equilibrium might be, a long time in a steady state, so nothing's changing and it's sort of flattened out. Like we usually think of that as equilibrium. The point is, an equilibrium model of the market does a good job predicting prices. It does a good job predicting design, so we use it. Okay. Take 2 years to figure out that that's a good model. Okay. What's output are basically what's called a counterfactual assessment. So the idea is, okay, if I had business as usual, and now I overlaid a CAFE standard, what would change? And that's called the counterfactual assessment. What would change are the sales, the prices of vehicle, and the designs. So you would know how many designs, or what the designs would be, how many of each designs were sold, and then if you made some assumptions about how much those vehicles are getting driven, you could figure out, first of all, how much fuel is being consumed, second of all, how much savings there would be for the consumer, because the fuel economy goes up. Fuel economy goes up, then there's savings in the use phase. And then you can figure out the environmental emissions from there, as well as, did the consumer win in the end or not. Or if you save more in fuel costs than it costs you to buy the car, then maybe you've won. But this is where discounting comes in, right? So it turns out consumers may have a 30% discount rate when it comes to looking at future fuel savings. And this is kind of common in the energy area, right? You following along to what this model is? The elements of the model. Again, this is a single period model, so we're looking at 2011. You could begin to think about dynamics, just like we talked about dynamic equilibrium versus static equilibrium in our basic economics examples. If I'm going to look multiple periods down the road, maybe I'll take a loss this quarter to make a bigger profit down the road. We're not looking at those issues here. It's a single period model. Okay, but hopefully at this point, I said it at the beginning, but hopefully it's becoming a little bit clearer. What elements ought to be in an analysis of an energy standard. Okay, like you could think of fuel economy standards being an energy standard, right? You got these different sides of it, and there's a lot to think about. And I'm also making the argument that the state of the art really hasn't figured this out very well yet. Okay. So 2 challenges now, summarizing. I've said these already. First, that there's engineering trade-offs between fuel economy and acceleration, and suppliers can basically tune how they land their acceleration fuel economy by adding new technologies, and that needs to be considered in an analysis of how effective a CAFE standard is going to be, or whether cars are going to get bigger because of a CAFE standard. So there are engineering trade-offs that nobody's really addressed before, and then this idea that if companies are going to take on technologies that are uncommon today, then we really need that engineering design component. Okay. So walking through here now, the things that need to be thought about, beginning with the product development process. Okay. We've talked about the importance of focusing on the medium term, and the idea here is that, and this gets into some technical issues here, but basically describing the product development process as a three-stage process. So you don't decide the price first and then figure out the dimensions of the car. Okay, so this is sort of your order of operations for product development. You begin with a concept that has the vehicle segment that this car is going into. You've got a certain powertrain architecture going on there with certain dimensions. And then the concept gets approved, and now you say, okay, well, we're going to design the engineering subsystem. We're going to make a 4-liter engine versus a 3-liter engine. It's going to have a certain number of cylinders. We're going to throw some technology on there. Maybe there's going to be some cylinder deactivation. You don't do that up at the front, and you can't change it after you've started production. Pricing occurs after production, and if you pay attention to these things, you see they change, right? This is important because if you're going to estimate a model, if you're going to try to figure out characteristics of the market from market data, you need to be able to tease out some factors relative to others. So if you know that at this point or at this point here that some of these things are static, it actually, from a technical perspective, helps you to perform a better estimation. So without really saying any more about that, what this product development process allows is for fuel economy and acceleration to be figured out inside the model, or endogenously, means inside the model, and prices to be figured out inside the model. But step A up here is outside the model. Okay, so there are assumptions about which cars are being built, not once you've decided to have a car in the compact segment, then maybe what the engine size is. So the model's doing the engine size thing, and it's not figuring out what a compact vehicle is. Okay. So model is now looking at fuel economy and acceleration responses to CAFE standards. Obviously, prices are a big determination there because that's going to determine how many of the vehicles are going to be bought and sold, and therefore whether the company is actually complying with its CAFE standard. Okay. Make sense here? Go ahead.
Just the medium term, I think you said it earlier, but I missed it. Is it the short term, there's not enough time to, for the benefits to outweigh the cost, and the long term is too complex? What's the
In the
choice
short
on that?
run, firms can only change prices. Cars are already built, think of it that way. The dies, everything's bought, so all you can do is change prices. In the long term, you can decide, you can change step A up here. Right? You can decide to compete in only the small car market if you want. You can do that in the long term. Right? In the medium term, you've kind of decided, which segments you're in, but you have some flexibility with respect to design. So that's what we mean by medium term. Other questions? Thinking about equilibrium already, I mentioned the difference between a static model and a dynamic model. We're looking at firms, there's 20 car companies that Katie modeled here, thinking about them as profit maximizers. And you could ask the question whether companies are really out to maximize profit or not. And you might say to yourself, well, is that really how they behave? they haven't always maximized profits, but the point here is that you could think about other ways of behaving. You could try to maximize market share because you think down the road it's going to get you more profit, right? So technically speaking, the world doesn't have to be this way. It is intuitive. It's a good model of the market, but it's enough of an assumption to make it worth writing down. Model is static versus dynamic. Okay, some math. Don't get scared. This is not anything tricky here. This is profit. This is one firm. J are the cars that the company is planning to make. So maybe I'm a car company and I have 75 vehicles or 100 vehicles, and each of those is a J. I have a quantity sold for each of those cars, and for each of those cars it has a price and it has a cost. So it makes sense that profit is going to be the price you get minus the cost times the number you sold. And then you just look at that for all the cars. Maximize the profit. You're going to make sure that this is subject to any regulations, like the CAFE standards. And then there is some technical business going on here. Basically, what Katie shows through some engineering reasoning is that you can basically create a function of the acceleration of the vehicle plus the technology that's been slapped on it to figure out its fuel economy. EFF is efficiency. Okay, fuel efficiency or fuel economy. Okay. What this says is that there's some fixed and variable costs, and you can figure that out as a function of the acceleration and the technology. And then your quantity demanded is going to be a function of the price. It's going to be a function of acceleration. It's going to be a function of the fuel economy as well as the structure of the market. Okay, so yeah, to understand the details here, it's a little bit to think about, but nothing is particularly counterintuitive that's going on. And as I said already, that was one firm's profit function. Well, there may be 20 firms there. So what she does is start with an initial condition. So let's say there's 500 cars, and let's say there's just 10 firms, so I can do the math in my head. So that's 50 cars per firm. So what do? Is I go ahead and I just initialize the run, and I say, okay, they have a certain gear ratio, they have a certain engine size, they're using certain technologies, and that means directly out of that there's going to be an acceleration, there's going to be a fuel economy, there's going to be a set of prices, and a certain profit. And that's just like an initial guess. It's not coming from anywhere. Right? So you initialized all the firms. Now, firm 1 is going to look at the other 9 firms, because I just said there was 10 firms, and say, okay, well, given their initial condition, here's my optimal set of prices, here's my optimal design. Okay, and then firm 2 is going to look at what firm 1 did, and then the other 8, and make a decision for firm 2's self, right? And then firm 3 is going to do that, and firm 4, and it's going to go around and around and around for about a day, if you're lucky, maybe 2 days, and you're going to converge on an equilibrium point. Okay. So in Katie's model, there were 20 firms. Make sense? Sorry? They're the vehicles. Tech is the technology options. I'll talk more about this in a minute. Pete? Does this have anything to do with game theory? It is game theory. Yeah. Yeah, so the equilibrium's Nash equilibrium. Anybody see the movie A Beautiful Mind? Yeah. All right, good. So a lot of nodding going on there. So that's good. So we've got now a model of equilibrium. Now we need the engineering design model and the consumer utility model. And everything I've set up to now turns out to be pretty easy. And what these 2 boxes, like especially figuring out how to do it the first time, that was maybe worthy of 2 PhDs. So, if you just look at the technology combinations, let's just take, what do we got here, 7 or 8? 1, 2, 3, 4, 5, 6, 7, 8. 8 technologies. Okay, so basically I've got 2 to the 8th, combinations, right? So maybe I've got 256 combinations of technologies. And each one of the combinations is going to have a different cost, and it's going to have a different impact on the performance of the vehicle. And the market's going to respond differently to every one of those. So you can imagine that this, if you just try to brute force this, enumerate this, right? Just to put it in perspective, you'll remember the coffee maker disassembly problem, where it's going to take 16 years just to look at the disassembly combinations. Like this maybe has fewer innate combinations, but because you got to run this game theory every time, forget it. There's no way you could just brute force this thing out. So what Katie needed to think about was, well, a bunch of things. Okay, one is, how are you going to code this problem in a way that is realistic but can be tackled by a computer? Okay. Well, the first thing you do is, like we did in the disassembly problem, is you look for just the combinations of solutions that make sense from a cost perspective. So if I've got 256 combinations I can put on any one of these vehicles. So the largest firm has 116 vehicles that it needs to optimize them on. I'm only going to look at maybe it's in the compact segment. Maybe I'm only going to look at 70 of them because they're the ones that are cost effective. And the other 180 or so, those are not, they don't make sense to do, because in any one of those cases you could pick one of the 70, it would be better for the same money or less money. Okay. So she had to establish the the cost-effective combinations of technologies. She also then needed to map those technologies onto each segment. So what she did was she looked at 7 vehicle segments defined by EPA, and then modeled a representative car. So maybe it's a Civic. And for that representative car, then, without any technology on it, let's figure out what the trade-off is between acceleration and fuel economy if I just change the engine and the gearing. Right? And I may not have every one of these options here, but I can model it as a continuous curve. So by having continuous curves, the optimization is a lot easier. If you just look at discrete points, it becomes a nightmare. Okay, so that's part of what's going on here. And then you can work your way down, if you want to sort of break out of this curve and you want to do better in both acceleration and fuel economy, well, you slap a technology package on there. So maybe it's technology combination 1 gets you this curve. And technology option set 2 gets you this curve. Okay? So, and the last thing to mention is then after you're able to, not only produce the first curve with your baseline vehicle, but then, model how these technology packages would look if you slap them onto that baseline vehicle, you would then, think about what the costs are. So, what is the cost of being here? Is it roughly the same as the cost being here? And then you would construct a cost curve this way. So she's taking a bunch of discrete numbers and making them continuous, just to make the problem tractable. Yeah. So that's the big picture, right? I mean, you're never going to get to, zero fuel consumption at instant acceleration, and your costs are going to go up maybe exponentially as you go down this way. Making sense? Go ahead.
Just a side point, where do these technology curves come from again?
They come from EPA and they come from NHTSA, and they're built upon a model of the vehicle. So the baseline data for these 7 representative vehicles. Came from a program called AVL Cruise. And then for a bunch of the technology, she actually simulated them in AVL Cruise. And then she also used EPA and NHTSA data. So NHTSA is the National Highway Transportation Safety Administration. Okay. So looking at the baseline model here, these are the representative vehicles. Okay. And I've mentioned already the engine size, changing that, changing the gearing. Oh, and the curb weight's an option here too. Curb weight wasn't a decision variable, but it was one that she carried along in her simulations. And again, about 30,000 simulations. All right, so that took some time itself. Okay. The costs also came from EPA and NHTSA. So thinking about now, this was the class project actually in 589. This was part of the class project. It's figuring out how engine costs vary with size. And then looking at, from the literature, the cost of technology features. Okay. And if you're using 2 technologies, in her model, she's treating the costs as additive, so that there may not be an efficiency between, say, turbocharging and cylinder deactivation or something like this. And there's some support in the literature that this actually makes sense. But Katie was not using the secret store of data that companies might have on these actual costs. Okay. So basically, just talking here about the cost being additively separated here. So I mentioned this too. How do you get this baseline curve? These are her simulations, and maybe this is your Honda Civic. You're looking at the different engine sizes that might be simulated in AVL Cruise. Now let's change the gearing, the final drive ratio. You get these points, and some of these points are dominated by the efficient frontier. So here are the optimal points, the best you can do in fuel consumption and acceleration. Now let's draw a curve through it, right? And you can, with that curve, both the gearing and the size of the engine. And the assumption here is that what the gearing is doesn't really matter, because that's not taken as a cost in the model, but certainly the engine size is. And it's monotonic. If you've got a smaller engine, it's going to be more fuel efficient. The acceleration is going to go down. If you got a bigger engine burning more fuel, you'll get higher acceleration. And acceleration, this is the, well, I'm going the wrong way, aren't I? So yeah, this is fuel consumption on the y-axis here. And I should mention here, this is not miles per gallon, it's gallon per 100 miles, okay? So this is fuel consumption, it's not fuel economy. I've been using that interchangeably here. So this is basically 40 gallons to go 100 miles, so it's more fuel efficient down here. And up here, it takes more gas, but you get a faster acceleration time. So this is the time it takes to go from 0 to 60 in seconds. Okay, so I might have confused some people for a second there. But this is how that was done. And then what she did was, there's some information in the literature about, okay, if I put a technology on the car, it's going to improve fuel economy. But what there wasn't good data on is, well, I might affect the fuel economy, but what's the acceleration? And that's important in her models we've talked about. So she actually used the AVL Cruise to figure out what those acceleration values would be. So that's how she actually made these Pareto sets here. Okay? So the impact on fuel consumption for a technology came from NHTSA, a couple of cases EPA, and then she actually figured out what the acceleration impact would be. And that allowed the creation of these curves. Okay? So I basically said this already, right? You've got the baseline vehicle, and then you've got levels of this technology variable. And then she's treating this technology variable as if it's continuous. So there's really two things going on here. One is, when I explain it, it sounds like a lot of work, but it sounds doable, and that's true. But one of the contributions was actually thinking through the process to achieve this, and that was not easy. We hit a lot of brick walls before we came on this. Okay, does it make sense? Basically, what's going on in the engineering side of the equation? What needs to happen? That's why engineers need to be involved. We didn't have costs, and the further we got into this, the more we began to realize that maybe the people who are actually making the decisions about design, they may not fully understand the costs either. And so, we basically, from the outside then, we built our own model for both fuel economy, right, it's called EFF here, and cost. So K's are model parameters. You don't want to ask how she got this model form, because that model form is just brute force. Let's figure out what works. You see some exponentials here. You see some linear terms. You see some quadratic terms. There's a lot of brute force going on there. But basically, as I mentioned already, you can, if you know the acceleration and you know the technology package, then you can figure out the fuel economy, right? That's because you've got fuel economy, you've got acceleration, technology package. You can figure out where you are in the space. So using acceleration and tech, I can figure out what fuel consumption is. And so basically, that's why you see tech and acceleration here. And she basically figured out what all the kappas were, as well as the model structure, right? And the error just comes from the fact that you're never going to get perfect match. So she did this with fuel consumption. She also did it with cost. And basically, I won't go into it in any detail, but these R-square values are not bad for such a complex system. So we didn't think that it would look this good in the end. We'll take it. I mean, you'd like 0.99, no doubt. But and probably that model form is out there. But considering all the things we're not modeling, we'll take it. This is what the model produces if you try to compare what you actually see for fuel economy in the market versus what you'd predict from her model. And it definitely follows the trajectory of reality, but it's not going to be a perfect fit just because of so many things that we're not modeling, right? And you may wonder, well, what are we not modeling? We're not really modeling, say, luxury features. You can begin to wonder, well, okay, well, is this programmed for, more of a sport mode or more of an economy mode, right? When you think about the shifting, it'd be an example, right? Just tires, right? We're not dealing with aerodynamics here. So there's a lot of things that are going to affect this that are not being modeled, and that's why there's a spread here. But doing a pretty good job here, capturing what's going on from the engineering reality. If you thought this was hard, I think you could follow that. This part, this is at least 2 courses in economics, maybe 3 or 4. This is a model of utility. So you're looking at utility here. Now you're seeing a lot of Greek. And by my estimation, there's 1 or maybe 2 people who actually know what this means that are in the room now. But basically, the idea here is, let's try to model the utility that a consumer would have for a given car. And then, there's no way to know, to observe utility. Utility is, I've got a car. I drove a Subaru today to work. What's my utility? I got no idea. And there's no question anybody can ask me for them to figure out what utility is. It's just not really a knowable thing. But what you can do is you can try to come up with some structure to the utility, and then say, just make an assumption that I don't really know what utility is, but I do know, or I'm going to make an assumption that consumers are going to try to maximize it. And under the assumption that consumers are maximizing their utility, and given the ability to observe the market, you could actually figure out what the maximizing utilities were and derive coefficients that say something about utility. So delta here is the average utility that is for vehicle J. So sorry, you're asking about the J's. So the J's are vehicles. And that's constant or average across all the consumers. But there are going to be variables that are not average across consumers. For instance, the interaction between vehicle attributes and consumer demographics. So before my wife and I had kids, we had a dog, and we like to, we have Michigan winters, so Subaru made a lot of sense, right? Then we had a girl, and then we had twins, and the Subaru has no utility to us anymore, right? We can't take 3 kids around in it, and the dog, forget it. So consumer demographics intersect with vehicle attributes, and beyond the average level, that demographic's going to have a pretty significant bias. So Y is trying to capture that here. Okay, so N is consumers, which are represented by their demographics, and J is vehicle. And the X's here, those are just product attributes that are not demographic in nature, and then you've got an error term. Okay. The delta itself is going to be made from things you can observe and things that you can't observe. So there's an alpha here that also needs to be estimated. Now, where this gets really tricky is that there are features in the system, leather seats, a certain styling, handling, noise, that really affect how much utility a vehicle has to a person that you're never going to observe. So you may have a confounding between things you are observing, like fuel economy or price, and things you're not observing, like luxury. So that's where your courses in economics come in, and this becomes an art form. And where something that doesn't look all that hard, say, well, this is just some Greek letters, I can figure it out in a day or two, becomes a lot of practice, a lot of research papers, and something that in practice is closer to an art form than a science. Nothing more to say. Okay. The utilities here that Katie looked at, she's thinking about price because price has an effect across the population of demographics. But if I'm a rich person, the price is going to matter to me a lot less. Okay, so remember the delta was what's average across the population. Price per income, that's a demographic interaction. Now, if I got a ton of money, so what? An extra $10,000, no big deal. Right. Fuel consumption, this is acceleration time, the footprint. These are variables in the utility function. And then, we've got our delta down here. So collecting a whole bunch of data on this, now you can think of these V's here as the U's. We're just looking at the utilities. Remember I said these new car surveys, they have the car that was bought, and then the second choice question of, okay, if you didn't buy that car, what car would you have bought? And if you didn't buy that one, which car would you have bought? And those data, a lot of those data were available to Katie. So basically looking at the one that was bought, the first choice, the second choice, etc., you can use that information to figure out what the alphas, what the mu's, what the betas essentially are. Okay, and there's some heterogeneity going on here that I'm not talking about. But basically, you use the market shares that maximize the likelihood that what was observed in the market in terms of market shares, first preference, second preference, etc., were actually met. So that's how it's done in words. Obviously, it's tricky. And in doing this, you can get a whole bunch of parameters. And when you actually do a sanity check on those parameters, you're glad to see that some things you would expect come out. Okay. First being that there are a lot of people who think about price elasticity. So if I change the price of the vehicle, then how's the market share going to change? So you can compare that with what other people did using different methods, and if you get numbers that are close, you feel good about that, right? That's good. You can look at whether the willingness to pay for improved fuel economy is less than the cost of the technology features. That's intuitive because if the willingness to pay for improved fuel economy is higher than the cost to put the technology on, you'd see it in the market already. So, you kind of have this sigh of relief when you see this, right? So these are sanity checks. It's not proof that this model is good, but these are the kinds of things you can do in addition to doing statistical tests, which I just blew over on the last side. Okay. What else we got? So, the loss in acceleration, it's basically key to note that consumers are less willing to pay for fuel economy than they are for acceleration. So basically, you see fuel economy has leveled off. After the CAFE standards are met, fuel economy basically didn't improve. Size got bigger, acceleration got bigger, right? And added features there were more added features to the vehicle, like consume energy, right? This is an important observation because if, consumers, in those coefficients that Katie got out, if they preferred fuel economy to acceleration, again, you should have seen that higher fuel economy in the market. Right? It should have been there already. Right? So basically what she has seen here are a bunch of characteristics that are supported by market data. They're supported by other studies. But it's not an out-and-out proof. Okay? But they are the kinds of observations you want to make. Okay? So, economics, it's an interesting field, right? Because, we've sort of expressed it up to now as a field of these linear curves that intersect, and, there's this single price for the market clears, and, it's all kind of quantitative and seems pretty straightforward. At the end of the day, it's quantitative and an art form, and it's a very hard business. And, you see, obviously there's a quantitative part. You got to figure out these model structures. You need to go get these sources of data. You need to make estimation assumptions. You need to, this whole issue of unobserved variables being correlated with observed variables. You got to sift your way through that, and there are methods to do that, but that's all economics. And it's not sort of run-of-the-mill stuff. It's hard. So, when I say that, when I started off the presentation today, saying, well, these economists haven't thought of design, I hope you didn't get the idea that they weren't smart enough to do it. They were. But they're busy tackling all these other challenges associated with these kinds of studies. It is not easy. Okay? And that makes, I think Katie's work even more impressive because she's able to understand both and actually integrate them together. It's non-trivial. Costs, so I've talked about technology costs. I talked about, that 589 project that told us how engine size might be related to the cost of an engine. And I talked about NHTSA and EPA data that might help us understand what the costs might be for technology packages. But I didn't talk about the cost of the vehicle. Where does that come from? Well, basically, that comes from looking at the existing market, existing vehicles, right? Everything besides the engine, besides the technology. Right? We need to understand those costs. So that comes by looking at the existing market. You assume that the prices, that companies have set their prices to be profit optimal that means you know the quantities, you know the prices. You can then figure out the cost by applying first order conditions, right? Take the derivative, set it equal to 0. There's an equation that needs to be met there. And then by applying a certain structure to the cost equation, you can then figure out what the costs are. Okay? Again, not easy, but it's doable. Okay? So, and those costs are going to depend on whether you're constrained to CAFE or not. So here's another wrinkle. Not all firms constrain themselves to CAFE, right? You've got some European automakers that are willing to pay the CAFE fines because they're not very high. You've got the domestics that do pay attention to CAFE, naturally worried about being sued, and they just meet it, whether out of moral or financial or legal concern, right? Then you've got some Asian firms that are way above the CAFE standard, don't have to pay attention to it, right? So the cost structure needs to be considered there before, some of those costs are penalty costs and some of those costs are actual vehicle costs. So you need to be able to back those things out too, and she did it, okay? So, and this is where I'm going to end. I'd hate to just present to you a CAFE study or a footprint study without giving you some idea what's actually going on there, right? And we've done that. Now we can have the fun. We can say, okay, we've built this machine. Now let's go stick a CAFE standard in there and figure out what happens. So we're going to look at 2 case studies. The first is looking at the CAFE standards as they're applied in 2014. So let me just get this thing working. And so looking at what that regulation is, so I think we've talked about the corporate average fuel economy standards enough in class. You know that they've been kind of stuck at 26.5 for the passenger cars for a long time. And the idea here is now, starting in 2012, they're going to ratchet up. And what Katie did was she looked at where those standards are going to be in 2014. And what it's all about is, if you're an automaker, you sell different cars, different trucks now, you can basically take the sales weighted mix, and you want to make sure that that average sales weighted fuel economy is higher than a baseline level, 26.5, going up from there. So one of the recent reforms, in addition to increasing the standard, was making the targets based on the footprint of the car. So you look at between the wheels, between the axles there, and you get a footprint. And if you have a larger footprint, your target goes down. Okay, and that would look something like this. It's a little bit small. I'll show you a bigger version of this in a few minutes. But this is a vehicle footprint over here on the x-axis, and the y-axis fuel economy. So you see that it's level, and then for the light trucks it comes down. Slopes are a little bit different for the passenger cars and light trucks. So, oh, the other thing is credit trading. So if you do better on cars, maybe you can give a bit on the trucks. So we've talked about tradable permits, same kind of idea. You can do credit trading between the passenger car and the light truck standards. Okay. So there's 2 strategies we mentioned last time. One is to basically change some prices, right? So that's what we're trying to show here. A couple of Ford vehicles. Taking the 18 mile per gallon light truck that has a target of 27.9, raising its price because it's well below its standard, lowering the price of the other light truck that has a fuel economy above its standard. Okay, so that way you can mix shift. You can try to exploit the price sensitivity of consumers, and works like a charm, but it may not be the best thing to do, as we talked about a little bit last time. The alternative is you change the design, and we talked about the difficulties in terms of modeling this from an econometric point of view last time, and that being a big part of Katie's contribution here. So the case she's making is that the short run may overestimate the cost, because it's certainly it may be cheaper to do this than it would be to do this. So basically we need some studies that look not just at the short term, but the medium term. And she makes a case that the short term may not be relevant anyway because firms are generally given 3 to 5 years warning so they can actually make the design changes to comply with the CAFE standards. Okay. So what she did in her work, again, she's looking at the 2014 CAFE standards. You can't read this, but I just included the table because I realized it wasn't there. Thank you, Roy. Thank you very much. This old school thing, this is great. Basically in 2014, rising from 33.3 miles per gallon, this is in the passenger cars, up to 34.9 by 2014. Okay. What she did was, given the data set that was available at the beginning when she started her work, we had 2006 cars. And she looked at roughly 500 vehicles across 20 firms. And they're then taking that 2006 fleet now and saying, okay, we can make some design changes. We can add these technologies. You remember these technology packages. And we'll figure out which vehicles get which packages. And she looked at 4 different cases. Okay, one is basically thinking about the medium run like we've been talking about. She looked at taking the credit trading out. So this is just sort of modeling the policy as it is. She looked at taking the credit trading out. She looked at taking out the credit trading and ignoring the trade-offs that occur between acceleration and fuel efficiency. So in other words, this is another sort of tough point in some of the analyses that have been done before is, you can make vehicles more fuel efficient, but and a lot of the times the acceleration is going to go down. That's going to affect market share. So what she wanted to do was sort of decompose that effect. So she took out the credit trading, then she took out the trade-off issue there. And then she looked at only the short term and what that would tell you. So the idea was, what can this methodology tell you about how important is this credit trading? And how important is it to consider these engineering trade-offs in the sales? And then how important is it to look at the design at all? Okay? Does this make sense, what she's trying to do here? So we can look at interesting things, right? You can remember she had this heterogeneous demand model across the population that she created. You can start to look at who is buying which vehicles, which technologies end up on which vehicles, what's the overall effect. It's really fun for the whole family, right? She looked at, I think we talked about this last time, the firms that are constrained to CAFE, and then the firms that actually pay the fines. Okay, so you've got some firms that are more than happy to pay the CAFE penalties because they're not that high. You've got other companies, particularly the big 3 here in the U.S., that are constraining themselves to CAFE. And you've also got some companies in Asia, your Hondas and Toyotas, that they're above the standard already. So the standard doesn't really matter to them now, although as these standards go up, it begins to. Okay, so sorry for the wacky slide changes there. This is just an example of the kinds of results you can get from the methodology. You can say, all right, and this is just skinning the cat. You could look at all manufacturers versus domestic automakers. You could look at specific companies if you wanted. This is looking at the percentage of vehicle models that take up different design options. So remember, she was looking at, I think, 7 different technologies, and you can begin to say, okay, well, the domestic automaker is going to take up basically all of these more than the auto industry as a whole, right? Now, it's saying, you should walk away with this as being a result. This is an example of the kinds of things the methodology can tell you. This is, I think, one of the big contributions of her work. So if you look at how EPA looks at environmental regulations, I think most of you have heard of this idea of costs and benefits, right? So we look at cost-benefit analysis. And the benefit has to do with the consumer willingness to pay, right? So what is a customer willing to pay for a 1 mile per gallon increase in fuel economy? And they're looking for a number. And you can go into the literature and you just see like all these reports with all these different numbers. And what Katie suggests that I think will resonate with everybody is that number doesn't exist. You know, that number is going to be different for you. It's going to be different for me. It's going to be different in different segments. And really, there's a distribution across the population, right? I mean, if you think about the fact that fuel economy and acceleration are related to one another, right? You know, you look at these European vehicles, right? You know, where you've got maybe a high, acceleration and very expensive cars. You know, you could think of that as actually, where your miles per gallon is actually a negative attribute, right? Because it's really the people buying those cars are only concerned with acceleration, right? So now teasing those effects apart, you see that, some people aren't willing to pay very much for fuel economy, and some are willing to spend a lot, right? And look at these people buying these electric cars. I mean, it's not rational when you stop and think about the cost benefit, right? So if you want to represent the market as it is, you have to look at the population heterogeneously and start thinking about willingness to pay as distributions. And she's done a really good job of that. And if you look at just the scale of the x-axis here, this is willingness to pay for a 1 second improvement in the 0 to 60 time. These numbers are pretty high. It's like, this is 1,000 and this is 10,000, right? Now, obviously the units aren't the same. This is 1 mile per gallon. This is 1 second. Question?
My question actually was about the units. I was just going to say it seems maybe a bit misleading to put 1 second for the acceleration, because that could be like a 20% improvement in your acceleration from 0 to 60, whereas 1 mile per gallon increase is maybe like, a 3% improvement in your fuel economy. And so it would make sense that with those different improvements that the dollar amounts would be.
Well, it would, except, we're not generally talking about, 10 miles per gallon, right, or 20, right? It's a lot easier to get 20% on this side than it is on that side, right? So, and these days now we're talking about new strategies and what have you, but, the proportion of people is actually very small over here. If you start looking at the percentage equal, it's a very low percentage relative to this one, right? So, yeah, that's why I was pointing out the units are different, but still there's a strong desire for acceleration. I think that's the key point. Other questions? Now, this is a table that I present not because of the numbers, but because, again, of the kinds of things that this type of analysis can tell you. So it can tell you, first of all, how much fuel is not burned when you put the CAFE standard on versus not having it on. You can look at how these technologies are being applied. So, there are certain things you can do to increase acceleration, certain things you can do to improve fuel economy, certain things will affect both, right? So the question is, when I'm adding a technology, am I using that technology to only improve fuel economy? Because that's what most of the studies assume. Or would some of that technology actually be tuned into acceleration? And the point of that is, if I'm just increasing fuel economy, it might turn customers away. So maybe I should take a portion of that and actually gear it towards acceleration. And so what it tells you, and it's not the actual numbers, I'm talking more about the magnitudes here, is that some amount of the benefit that you get in by applying technology to reduce fuel consumption is actually eaten up by the use of that technology or technology to improve acceleration, to get market share back. Okay. You also see a large number here. This is your mix shifting. So I don't want to say that companies don't adapt their prices to get more people buying higher fuel economy vehicles. They do. But the design's also important is the point. Okay. You can also look at the rebound effect. So as you increase fuel economy, people are going to drive more, generally. And you can take certain assumptions about it, and you could compare the magnitude to this magnitude, and you say, okay, well, the rebound effect probably isn't all that important, right? You can slice this by the automakers as well. So you got the big three, and the folks over in Asia who are above the standard, the others who aren't, and look at the impacts of the regulations on them. Here's an example of a positive consumer surplus. That's generally not going to happen. This is where consumers actually benefit a lot because this is billions of dollars here from the policy. Generally, there are going to be some increased costs, and this number is going to be negative. It just happened that the table I had one example in it that was positive here, but generally that's not going to happen. So again, don't take away the numbers here, but the kinds of things you can say, all right, consumer surplus, I can break that down into prices, into attributes, I can look at profits, all right? So, this way you start to think, I'm sure all of you are thinking, it's like, okay, well, if the U.S. government's making a policy for the U.S. market, maybe it's thinking about how to increase fuel economy in a way that maybe it doesn't hurt U.S. companies as much, right? So that kind of analysis can be done. Now, the example I do want to show you with numbers is looking at the 4 cases that were outlined a few minutes ago. So looking at basically Katie's simulation of the policy and just the short run. Let's start with the beginning here and the end. So if you assume that the only thing that producers can do to get people to buy vehicles with higher fuel economy is to change the prices, this is going to be very expensive for producers. Okay, so that's like $149 billion, and some companies can't even meet it. If you look at the ability to also change design, you're almost 10 times less, or maybe 9 times less, in terms of the cost. So, being able to incorporate design into the analysis is important. I think that, when you compare this number to this number, it's pretty clear. If you look at taking the credit trading out, turns out the credit trading is, it depends if you think $4 billion in a year is a lot of money or not. By percentage, it's not a huge number, maybe 20% or so. If you take the trade-offs out, right, you see that the ability to trade off acceleration versus fuel economy, that still a higher number, almost twice that of taking the credits out. So the point is, design's important. And there are a lot of things you can do with this kind of analysis, okay? In the end, you might be interested from the environmental perspective. This is sort of the economic perspective. Are the full fuel economy gains going to be seen or not? Okay. So basically, what comes out of the analysis is that shifts in what's produced, that's about 38% of the gains, and about 62% of the gains are actually due to changes in design. So again, design's important. Domestic firms increase their fuel economy by about 4 miles per gallon relative to where they were on the 2006 case. Okay. So one thing that came out of this is that you've got, as the domestic firms increase their fuel economy, there's essentially attributes left on the table that are performance attributes, acceleration in particular, okay, that previously was being met by the domestic firms, but now they have to increase their fuel economy. And there's a question as to whether the firms that are already above CAFE are going to swoop in and start making muscle cars, basically. Let's take Toyota, let's take Honda, and say, oh, actually, without violating the standard, they can start to kind of come in and take that off the table, if you will. So what she saw in the simulations was a pretty strong shift in sales to foreign firms that was sort of resulting from this increase on the basis of higher fuel economy and the domestic firms constraining themselves to CAFE. Now, just because the model says that this could happen doesn't mean it will happen, right? There's Honda and Toyota now above the standard. Maybe they're going to stay above the standard, right? But the point is that there is a significant impact for leakage, and that would decrease fuel economy by overall fuel economy about 1.5 miles per gallon. So should they choose to kind of violate the standard or come down to it based on where they are, then you're burning a lot more fuel than you would have otherwise, and their sales are getting picked up. So both of those effects are undesirable. But there's no instrument available to kind of keep that from happening, right? So one of the the upshots of this is that the reformed CAFE standard, it can be very beneficial, but it kind of depends on what firms who are already above the standard or who are violating the standard do, right? And you might say to yourself, well, that's maybe not the best way to write a law, where it just depends on what some foreign automakers decide to do. And they may or may not change. I have no idea. But when you actually stop and think about the implication of that, it's fairly serious. So that was one thing that came out that I don't think people were talking about, certainly not with numbers, before Katie's work sort of hit the prime time. Okay. So there's a potential for what the sort of technical term for it's leakage. So when you've got the ability for other firms to come in and pick up acceleration performance that the domestic automakers who are going to constrain themselves to CAFE, assuming they will, that could be what's called a leakage, and that might reduce fuel efficiency rather by kind of a lot. So instead of 33.9, you're going to be around 32 or something like that. So it's all pretty interesting, right? And what's nice about having a model is you can run different scenarios. You could look at the case where you do constrain those firms to CAFE, and Katie's doing that work, and she's revising the analysis and sort of getting ready to publish it in an economics journal. So that work's still ongoing, but you kind of get the sense of what kinds of things come out, and they're the kinds of things that previous work haven't said. So it's interesting. Questions? It's making sense. In the end, it isn't about the numbers. You don't go through 2 years of work because you think that fuel economy is going to drop 1.9 versus 1.8, or the overall domestics go up by 4 versus 3.5. You do it because you discover something that might be general, and you've got a very strong basis for it, and you want to alert folks to it. Right? So this leakage effect was fairly significant. Okay. And in her second case study, she had a different concern. Okay, and that was about cars getting bigger. So it stands to reason that if you tie the fuel economy standards to footprint, you say, well, you don't have to hit as high of a target if your footprint is bigger, that maybe a firm out there might decide to make a bigger car, a bigger track, going on there, bigger footprint. And there were enough people saying that wouldn't happen based on analyses that didn't incorporate the things we've been talking about for the last day and a half, that sort of begged for the analysis to happen. Okay, and that's what the second case study is really all about. It's about whether the implication or let's call it the implementation of the reformed CAFE standards will make cars bigger, and if so, would that sort of reduce the overall benefit from the environmental perspective of the policy? All right. Am I making sense? I have to ask you because I got no idea. So, so that's basically what's being said on this slide. So looking at the potential incentive. Go ahead.
Were there curves before these new CAFE standards? Like, how did they determine what the fuel economy should be?
So this is new. So this is with the reform standards. It wasn't based on footprint. So the reformed CAFE did that. Now you can ask how they got these curves, and they actually did an econometric regression on the market itself, and came up with these. Okay, you see they're flat out here and in the middle. Then that's just to keep it simple, draw a line through what they actually observe. Okay, but what that doesn't do, it does not incorporate. Just because you have a series of observations from the past, this CAFE standard didn't exist in the past. So there's nothing saying that what happened before with respect to producers' incentives to increase size would exist in the future under this new CAFE standard. So that's exactly what she's testing. To say now that we have this, we can now try to model the cost of increasing vehicle size. We can model the preference for larger vehicles, and let's see if more bigger vehicles are sold. Right? So this is, again, to use the word, a counterfactual analysis. So you look at people's preferences as they might exist today. You look at the vehicles that exist today. Now you just slap down the 2014 CAFE standard on top of that, and then you say, well, did the cars get bigger or not? Okay, so she's doing everything she did before with respect to the technology implementation, but now singling out footprint. So footprint was not a variable in the last study. The dimensions of the vehicle stay the same. Now it's going to be a degree of freedom. And we're going to see if the cars get bigger. So the formulation it's identical to what we saw before. This is profit maximization of each firm over all its vehicles need to satisfy the CAFE standards. And the only addition here is allowing now footprint to be a changing variable in the system. And because she doesn't want the analysis to get ridiculous, she said, we're going to limit the increase in size of any given vehicle to 10% or less. So that's what this constraint says. And she had basically, if I can think, about 3 things that needed to happen here. One was to figure out how footprint affects weight, because weight affects both fuel economy and acceleration. All right, so that was the first thing. The second thing then was to establish that relationship with efficiency. And then the third thing was to figure out how the cost of a vehicle changes with the footprint. And that turned out to be the doozy, because we have a lot of contacts in the industry, and as best as we can tell, nobody really knows. It's hard. We're talking small increase. We're not talking about the building a car versus building a truck. We're talking about changing vehicle dimensions by up to 10%. And what is the cost of that? So we'll talk more about that in a minute. Okay. The last thing that's implied here, so fourth thing that needed to happen, was figuring out what people's preferences would be for larger vehicles. So you remember that discussion about the demand model we had last time. And footprint wasn't in there as one of the models, or one of the parameters in the model. Okay, there was a good reason for it. It's hard. The data is not out there. So she's basically using a different demand model, where instead of trying to nail down sort of how different demographics of consumers would respond to footprint increases with respect to their willingness to pay, she took the widest range possible of that willingness to pay for increased footprint. So she looked at a small willingness to pay versus a large willingness to pay, and looked at all the values. So if you could show that for all willingness to pay for larger vehicles, as long as it's more than 0, that cars are going to get bigger, then it doesn't matter what the number is. And you don't have to spend another 2 years trying to get it. right? So this was handled, the willingness to pay for increased size, that was handled via sensitivity analysis, okay? And so basically the demand function changed from before, and those are details, and if you're interested, you can read the paper on that. So, you know, and I've kind of mentioned that she had to do this already, figuring out how the weight changes with footprint size. And, you know, what's interesting or what's of note here is it's not one-to-one. There, you know, a significant fraction of components of the vehicle that are independent of the vehicle dimensions. Okay. Some don't vary with footprint, but vary with the height. And when you add up the two, it's about 50%. So, you know, a 1% increase in footprint, and this is an assumption, results in 0.5% of increase in curb weight. And she did a sensitivity analysis of that assumption, of course. But the key thing is it's not one-to-one. It's less than one-to-one. You know, it's in the range of, you know, maybe 0.4 to 0.6 there. And that matters a lot, because if you assume that weight increases with footprint at a one-to-one kind of correspondence, then your incentive to increase footprint is going to be lower, right? Because if it, you know, just think about it in the extreme. If you increase the vehicle footprint a little bit, it gets way heavier. Then that's going to just reduce the performance across the board of the vehicle, right? So she had to do an investigation of what these numbers are likely to be. She did, between 0.4 and 0.6. Now, production costs, I mentioned, like, we really had no idea after talking with some brilliant people in the industry. You know, we just had no idea. So the assumption here is that costs increase with footprint at a one-to-one ratio. Now, you'd say there's no way it increases at a one-to-one ratio, because you've got, you know, body panels and glass and a bunch of components that just are not going to scale that way. They're going to scale much less than that. This was a conservative assumption, because if you assume that it costs more to increase the cost of a vehicle than it actually is, and you still see producers doing that in the simulation, it's like, even though it was more expensive in the simulation than it is in reality, in the simulation the producers still increase their vehicle size, you can be pretty sure it's going to happen in reality. So this was a very conservative assumption that was baked in here, just because of the lack of information that we had to model that appropriately. And of course, if it's less than one-to-one, then the footprint grows more. Okay. Make sense? All right, so now you get into some of the compromises you got to make when you're doing an analysis like this, even when you're doing your PhD on it. The other assumption, which we were told was a good one from people who knew, is that, you know, in the range of footprint that we're talking about, footprint variations, the fixed costs don't really change, because you're talking about this on a time scale where, you know, you're not you know, really going to be paying more for the capital up front just because the footprint's about 10% bigger, or, you know, 5% bigger or something like that. So we made a, you know, what we think is a realistic assumption here and a very conservative assumption here. So the demand parameters from the literature are all over the place. So we talked about price elasticity last time, so ranging from 2 to 3.1. So this is how, you know, if the price goes up, then, you know, how much less likely a person is to buy the vehicle. Expressed as willingness to pay, I think these are more intuitive. So this is per square foot on the footprint, you know, a range of $340 to $2,000. Acceleration is different here. It's not 0 to 60 time. It's expressed as horsepower to weight ratio. So if you have more horses and less weight, you're going to have more acceleration. Okay, but that's how it's expressed here, because most of the studies were taking it this way. They weren't using simulations the way we were. So $160 to $5,500 there. And now fuel economy in the range, this is not miles per gallon, this is gallon per 100 miles. So $800 to $9,000. Okay. So very wide ranges and looking at all corners of the space, running the simulation and asking whether cars get bigger. Okay. And guess what? She found that they do. Only in the case where people have a low preference for footprint and a high preference, at the high end, at the extreme high end and the extreme low end of fuel efficiency and acceleration, you see that the values on the other side is 0. In almost all the cases, vehicles get bigger. And the average fuel economy that's observed is 1.4 to 3.9 miles per gallon, lower than if sales and size were not affected. All right, go ahead, Joe.
Does the CAFE standard apply to gross vehicle weight or to footprint?
So you have different size classes. You've got the light trucks and you've got the passenger cars, and that's where weight comes into it. This is a footprint-based standard. So you've got different footprint standards for those two classes. So that's how weight comes in.
So weight is varied as an effect of footprint. If they don't regulate by weight, they regulate by...
They considered doing this by weight, but they didn't, and I don't know why. I have guesses, but I don't want to share them. There's actually one study that was done looking at weight a long time ago, which you might be interested in. Other questions? It's a good question. Go ahead.
Is there any historical data that you guys looked at? Because I happened just a week ago to be talking over Thanksgiving with my brother about cars, and he was trying to argue, and I haven't looked this up, that cars today are so much larger than cars 20, 30 years ago, that even though we've increased the efficiency of the vehicles and added catalytic converters and stuff like that, that we're still worse off because our cars got bigger.
So if you look at I didn't bring the plot. I think we looked at it earlier in the term where we look at the average fuel economy of the fleet. Basically, when CAFE was ramping, the original CAFE was ramping up in the 80s, you saw increases in fuel economy. Then the automakers met the target, sat there, and the cars still got more efficient. Absolutely, they got more efficient. But that efficiency wasn't being applied to fuel economy. You're just taking more mass around, more size around, more features around, and instead of burning less gas. And so that did happen. And you can show that in a lot of ways. Yeah, cars it's almost like Moore's Law. The cars get more efficient. It just doesn't turn out to mean less gas. Go ahead.
Can you explain again the distinction between a passenger car and a light truck?
I can't. I'd be embarrassed to even try because if you actually look at it, it's not a very simple thing. I should probably email the class sort of the text around that very topic. Is a Subaru Outback a light truck or is it a passenger car? Right? You start. This gray zone in the middle, the crossovers, it's a mess.
Crossovers coming into the market? Is a Ford Edge really a light truck, or is that a
What I can tell you is, and I don't have the answer to that question, but I can tell you that there is a prescription, and it's complicated. So if you take vehicle X and you put it into this prescription, you're going to get an answer to your question. Is it obvious or intuitive? No. So I would best just share that information with the class and then let you read it because I wouldn't trust myself to quote it. Other questions? Yeah, keep asking questions I can't answer. Right, this is this is complicated stuff. It's great. Anyone else? These are just more results. The key is you're seeing plus signs, under all these different scenarios. Now, I didn't mention that this 1.4 to 3.9 miles per gallon. This is 20 to 50% less fuel economy than you would otherwise have. So it's actually a pretty significant chunk. right? So you think that, you know, emissions are going to go down by a certain amount, but they don't go down by that much. It's, you know, it's 20 to 50% different from that because cars get bigger. And we did a back of the envelope calculation. If you just take like a standard like coal-fired power plant, it's something like operating, if you take the grams of CO2 equivalent that this is versus you know, what a coal-fired power plant would emit typically in a year, it's like 3 to 10 coal-fired power plants. So it's not, you know, it's, you know, the whole transportation fleet's a lot bigger than that. So you can say, well, you know, it's maybe not that much. This isn't, you know, this is 20 to 50% of the gains. It's not 20 to 50% of the fuel economy, right? But it's still more than people would expect because, you know, the fact is a lot of people said cars wouldn't get bigger because they drew these functions so that wouldn't happen. Right? We think it is going to happen. And we think there's a strong chance that something else is going to happen that is a little unsettling to us, but we don't, you know, we can't really prove that it's going to be a big deal or not. But when you look at the math of this, you can find, what you see is that the CAFE standard basically hits the trucks, light trucks, harder than the passenger cars. So the cost of complying for the light trucks is higher. So you know, they're not that thrilled basically for doing this. So you have on the bottom here light trucks. You have at the top here passenger cars. So for the light trucks, they're actually, you know, looking to, so the plus is the sales weighted average, fuel economy and footprint. Okay, and as I move to the right here, this is an increase in footprint, and this is an increase in the fuel economy. Okay. So basically what happens, the light trucks slide farther to the right than the cars do. Okay, so basically it's cheaper to take advantage of the footprint clause, if you will, for the light truck. You can slap technology on for the passenger cars. The point is that the trucks, which are already bigger than the cars, are getting bigger faster than the cars. And if you're concerned about crashes, where mass differences and size differences matter, then you're kind of creating a separation here. And you know, when you get into the world of safety, you know, it's a big food fight because it's really hard to model that stuff. But it is intuitive that this could be a concern, right? And her work pointed that out as well. Okay, so you know, and it is known that the safety risk is increases as the spread of the vehicle sizes get larger. Now, will this particular spread be a big deal? You know, we couldn't tell you that. But the spread is getting larger. So that's a concern. So basic, you know, conclusions is, you know, there's not only some possibility for leakage from CAFE to the foreign automakers that we have to be concerned about. Maybe that'll happen, maybe it won't. But there, you know, is, you know, basically across the industry some opportunity for footprint leakage, and it's not a very small thing. You know, again, from 20 to 50% of the gains by Katie's work there, and you know, and there's also this concern about safety. It would be nice if you were able to decouple these things, right? If you could put a constraint on fuel economy and a constraint on safety, that would be nice. But you know, it's really hard to do that. So you know, basically, you know, you can't just stick a computer model of a car. You know, you can't just put it into some safety software and get a number out, right? It's a very difficult business, and you know, decoupling these things, while it would be nice, is you know, not really possible now. Let's see if this says anything else. Yeah, so the basic upshot is, you know, we should probably be paying attention to these things. Sarah?
So a few slides ago you showed that the German automakers don't conform to the CAFE standards. Am I correct? Or do they?
Well, some do and some don't, but go ahead.
So the thought that's in my head is the consumer willingness to pay for acceleration would be higher, or would be higher for acceleration compared to fuel economy in that class. Is that the incentive for these automakers to not meet CAFE standards?
Right. I mean, if you're selling a luxury car, let's just generalize it, not to a country, but you're selling a luxury car where, you know, you're putting commercials on TV where the car is going around the Autobahn, right, zipping around, right? You know, probably the person who's attracted to that is, you know, thinking about that car zipping around, and they want to feel it when they get into the car, right? And therefore, you know, just putting technology towards fuel economy and reducing acceleration might actually hurt sales of that significantly, right? So that is what's going on there, indeed. So, you know, a lot of pain on Tuesday, but, you know, what comes out is interesting. And I'd like to be at a place where, you know, maybe 10 years down the road, this kind of analysis is so standard that, you know, we could be doing it routinely, right? And that's basically what, you know, Katie talks about. You know, we look at LCA now. We can look at, you know, input-output life cycle assessment. We can look at, you know, the International Standards Organization, LCA, thinking about single products and their environmental attributes, right? We know sustainability has three elements, right? Triple bottom line. It's got the environmental, social, and economic, okay? Some folks are out there working on social LCAs. That's a long way from being perfect. You've got economists that have done general equilibrium models. Where, you know, Katie's work really fits in is right here, right? So looking at an industry scale, environmental and economic considerations together. So we can call that an approach for evaluating environmental sustainability. So, you know, the question is, can you use this really for other products, right? And what would be the process for that? Well, you know, you can think about a policy instrument that affects technology and design relationships, thinking about producer decisions, consumer decisions, and so now you basically, you know, get to a point where you can model the different industries, the producer's supply side, the demand side, and then looking upstream and downstream, right? You know, what material and supply chain options do producers have? What are the downstream disposal options? And then you basically tack on the LCA at the end. That's what Katie did, right? In an upshot, this is the flow. But the question is now, and the point is, you know, if you can do this, you know, as long as you have the LCI data, you're good to go. You know, I think the question moving forward is whether we can now apply this to, you know, refrigerators and washing machines and, you know, consumer electronics and the like. So that's to be determined. Again, you know, there may be simpler products, and we can model their design reasonably straightforward way as long as you've got some data. And we've done refrigerator before even. But from an engineering standpoint, and maybe the costs you can even get, but what's the nature of the consumer side of it? You know, can you get the market data to develop demand models? You know, these are big questions. Right? So, you know, I wouldn't want to spend a significant amount of time talking about LCA, talking about consequential LCA, and then telling you there's no way to do it. I'd rather tell you there is a way to do it. Here's how you do it. It's really interesting, but it's hard, and there are a lot of things to think about. Right? And so that's sort of where the state of the art is right now. Questions? Sir?
For the consumer electronics product division, isn't the technology frontier too dynamic to really do an economic analysis of?
I don't, without trying, I don't want to say that it is. You know, there's a question, I mean, Moore's Law is pretty standard, right? Now, what designers might do with that is a question, right? Phones are really big, right? Car phones, you remember they say travel with a suitcase. You know, they kept getting smaller and smaller and smaller until it reached a size that, you know, shrinking it didn't make any sense because you lose it in your hand, right? So suddenly now, just like we were talking about with the car, you see those advancements being put in other dimensions, right? Can you quantify that? Can you establish a frontier? Yeah. Are you going to go 15 years into the future? No. But, you know, these end-use energy-using products directives, you know, they don't necessarily go out that far, right? So, you know, question is, you know, if you do a, you that would be a good example, like the energy using products, and what might its effect be on on sales, right? So you'd have to look at the attribute space very differently. You have discrete features instead of continuous engineering ones, right? So I don't want to say it can't be done. I'm pretty confident it can be done, but the data sets and what have you on the consumer electronics side, that's a lot harder than something like this.
That's true. I guess my point was more about the time it takes to do such an assessment. I mean, Katie took quite a few years to come up with this methodology. I think that's more than the time span of a particular technology frontier. So by the time you're done with the analysis, the industry's already moved on to something else.
Well, you want to be asking the right question. I mean, the point is that, are you asking a question that is so design dependent that, 2 years your question is going to be obsolete, right? If you want to look at recyclability, we don't have to talk about energy. We could talk about any attribute. Now, recyclability. Now, let's look at that over time. The materials being used, and you can apply the same thinking to that. Yeah, you definitely don't want to be having radical changes in your industry in the time frame of the analysis, right? And hopefully this becomes more of a standard. It's not like splitting the atom or something the first time, which it seemed like. Other questions? Go ahead.
Who do you see mostly, if this could be expanded to work or become more commonly used, who would you see using it? Would policymakers use it? Would designers use it in major companies for design products like you mentioned? I mean, clearly the people who made the original CAFE standards probably didn't do something this intricate.
All right. So this is targeted towards policy, because if you see, it's of interest to sophisticated, wealthy companies, because they may want to try to manipulate the policy, right? And they may want to understand implications so they can lobby the right way, right? But mostly this is about academics informing policymakers about how to achieve sustainability. You've got targets in an industry now, and if you're going to put policies in place that are going to leak, you're not going to hit your targets. But those targets are coming from science. They're not made up political targets per se, right? So they're supposed to be anyway, in theory. So I think it's it starts in academics. I think informing policymakers. What disciplines? I think engineers are well suited, because the technical parts of economics, it's a lot of math, and engineers are good at math, and they also understand the product in a way probably economists don't usually, right? So I'd like to see some engineers doing this kind of thing. But generally, it would be for writing papers and informing policymakers. Trying to get ahead of this instead of behind it. And so, actually, related to this, the new CAFE standards are coming out right for 2025, and the rulemaking process is going on right now. So we actually tried to get the footprint paper accelerated through its journal. So it's been accepted to Energy Policy, and you've got the reference at the end of the notes. We're going to try to do a press release just to get some attention paid to these issues. Right? It's not to say something's going to change because of it, but we're and certainly I should say that the folks who make these rules are aware of our work. We've talked to them several times, and they know and they get it. They wouldn't publicly, agree with what we're saying. So when you read about this next year, you're probably going to see this work admonished. But well, we can have that discussion offline. But the fact is that we got to get ahead of this, not sort of react to it in real time. Got another point? All right.
There, which was Holden something. Is that John Holden?
Yeah. Early on, right? He did the well, we call it the iPad equation or the master equation. Question? No. Just move your hand around. Okay. So, I put the references there. You've got, anybody's interested, readings 59 to 61 cover this stuff. Okay. Now, we've talked a lot about fuel economy. We have not talked a lot about materials, right? Has anybody, and I know some of our off-campus students are involved with sort of materials design for automakers. Is anybody aware of some of the advances that are being made in terms of the vehicle itself and the materials that are being used there? Joe, you got anything you can share with us?
It's like I've just been reading a lot about using high-strength steel that can help lower the mass, but still meets the strength requirements.
So, there's a concern with aluminum we've mentioned before, right? And that is that its production emissions are rather high. If you can lightweight using steel, you don't have the production emissions and you still get the lightweighting benefit. So there are groups working on vehicles made of high-strength steel. And I made a reference, actually, I can't tell you the reading number, but it is online. This is actually some work that we did looking at aluminum versus high-strength steel vehicles, the cost and the environmental benefits. There's actually 2 papers on that that we've done if you're interested in that topic. So lightweighting is key. What else? What's going on in Europe and Japan with respect to vehicle materials? Go ahead.
About how the rare earth metals are becoming an issue in electrification of cars in the future?
I was not, but that is an issue. So, that's certainly something to be concerned with. Where is lithium coming from? What's the supply chain of batteries? That is very hot in the news right now. What other aspects of materials? End-of-life vehicle directive. Anybody heard of this? We should probably spend a minute on it. I was going to guess that most people knew about it, so tells you what I know. All right. And there's a similar rule in Japan. Basically, in the U.S., about 82% of the mass, and different people quote you different numbers. I've heard below 80, I've heard 85 before, but basically somewhere in the low 80s, let's say, percent of a vehicle gets recycled at the end of its life. And in Europe, there is the end-of-life vehicle directive that is basically increasing the rate of reuse and recycling. Reuse and recycling is over here, 80 to 85%. So this is sort of recovery targets. This is by mass. In 2006, going from 85 to 95%. So what this is saying is of all the mass of vehicles being retired out there, you got to bring back into the technosphere 85% of that mass or 95% of that mass. Now, of that mass, the percentage of components being reused or recycled is 80% and then 85%. Okay, so these are fairly significant targets. And so, and you can't make the whole car out of metal, right? You're not going to make the seats out of metal. So, well, the frame is, of course, but I meant the cushions. So there are going to be plastics in these vehicles. Plus, plastics are, light, so, there's, lightweighting and use phase benefit of that, right? So there's a big move that a lot of people are involved in to try to figure out how to take, old plastics from cars or even from other industries and then convert them into components for vehicles. Okay, so I think there's a slide from Ford I have here that just gives some examples of that, right? And all the companies are doing this. Okay, but thinking about renewable materials in the vehicle, and then what happens at the end of life, ranging from reuse to recycling. So there's a lot of work going in this area. So we shouldn't we talk about CAFE standards for a class and a half. I don't want you to walk away not being aware of all the work that's going on across the industry. U.S., Europe, and Japan, to figure out, okay, you got this vehicle coming in, what can I do with it, right? And if I'm making a new car, what components can I use that is input from either old vehicles or other waste, right? Could be soda bottles, could be old tires, could be carpets, right? Old appliances that are finding their way into new vehicles. Okay. So what's different about the materials than the CAFE standards, right, is that, yeah, there is a push. There is regulations in Europe and Japan, and the U.S. automakers build over there too for those markets. So they got to pay attention to it also. So there is a regulatory push. But when you stop and think about it, most of these components are not directly observed. So they're good spots, if you want to make the carpet out of old soda bottles. Well, great, because the consumer probably isn't going to know, and it's cheaper. Right? So there's a lot of this work going on. So in addition to what we see in the use phase and powertrain and lightweighting for higher fuel economy, there's work going on for recovery, for reuse, and designing for that recovery and reuse. So that involves how do you disassemble the vehicle? If you have two plastics that are similar in the vehicle, can I either design to just use one, or can I develop a technology to separate those two, even though they look similar at the end of life? Can you use recycled materials, right? Whether they're recycled from other old vehicles or from other industries. Renewable resources. This is flashy. We're going to make seat foams out of soy. Not always. Maybe the wisest thing from a life cycle assessment perspective, but certainly the idea of using renewable resources is attractive, and that's a selling point for a vehicle. Expanding utilization of used parts or reuse, reducing substances of concern. So you remember on the review for exam 1, I talked about the REACH directive. So substances of concern is what that's all about. So so the ones that are regulated, called substances of concern here, trying to figure out how to reduce those. And then, deploying recyclable structures for vehicles. If you could think about that, this is way out there, right? Because you got to worry about the safety. But, using Joe's example of high-strength steel or aluminum, those are highly alloyed components. If you have a body in white that's light-weighted, the opportunity to recycle that material into exactly the same body, if you will, or the same aluminum grade that can withstand a crash, that's beyond the reach of engineering right now, right? So they're working on that. So if you put all of it together, we're talking about the production phase, and we're talking about the end of life phase, which I thought was worthy of mentioning here, because when we talk about cars, we're so worried about global warming, we talk about air pollution, right? We talk about gasoline and where that comes from. Certainly want to spend at least a few minutes here talking about the materials and end-of-life issues. Right? So it's a tricky system. And as we conclude here, I want to go back to a slide that was related to what Sarang presented here, and I just want to talk for a few minutes about it. If we're going to reduce greenhouse gas emissions by some factor, but we're talking generally 80% by 2050 if we're going to avoid that what's called dangerous anthropogenic interference. So talking about 2 degrees C roughly for greenhouse gas emissions. The question is, how do we do that? Right? We've got technology. And I really like this slide that he presented here. So all these different things that we could be thinking about, right? And I guess what I'd like to start the discussion by asking the class is, if we just take the auto sector out, let's say we're trying to get an 80% reduction just in the auto sector, not economy-wide, but just in the auto sector. How many people think that it's possible to do that? Just taking a vote. Everybody understand the question? 2050. 80% by 2050. The question is, how many people think that we have the ability, I'll call it technologically, to reduce greenhouse gas emissions from vehicles by 2050, 80%. Okay, let me ask it the other way. How many people don't think we do? Okay, so that's a minority. So let me ask that group. What you think is keeping us from being able to meet the 80% reduction from a technological perspective? Go ahead, Nicholas.
Behavior.
So we're going to drive more? Is that the main issue, or?
Don't care about actions. It's all about consumptions.
So the question was asked a little bit differently. It was about the technology. So I was trying to save that for the next question, right? You can ask if the technology exists, and then you can ask, will it happen? Right? So if I were to ask you, do you think the technology exists to do it? You'd say yes? Okay. Does anybody say no?
I mean, I wouldn't say no. I would say I'm not too sure. I have my doubts, because if you look at the technology available, it would be from IC engines going to hybrids or going to electric vehicles. So you're basically offsetting your carbon dioxide emissions by power generation. By power generation. And right now we produce everything using coal. I mean, a lot using coal. So we'd have to completely switch to nuclear or other things that are carbon neutral. So whether that is technologically possible by 2050 when we have such a huge demand, and where there is variations in demands.
But we have nuclear, we've got wind, we've got solar. So technologically, I think you're saying we can do it.
Wind and solar, I wouldn't count, because because today battery technology isn't sophisticated enough for us to actually use wind and solar like we use any other. They're must take. So I wouldn't count wind and solar as possibilities. I'd only count nuclear. So do we have the ability now, to take, to take consideration of the, variability of power demands and things like that? So I would say,
you should look at where wind has been deployed to a significant amount, and it can take a bite out of it. It will not be 100%. There's no doubt about it, and certainly in a place like this, you won't get much solar. But thinking about it, but I think you're saying the technology exists. You're saying it's got to be nuclear, 100% nuclear, because that won't happen, right?
that's what I meant. If we have to use solar and wind, they're intermittent, and if we have to use them, we'd have to develop some sort of storage mechanism. And batteries, flow batteries, these seem the most promising. The technology today, you asked, that isn't advanced enough for us to store that mass of electricity. So the only thing I could think of.
You don't want to be pumping water.
Yeah.
With it. Yeah.
It's too much.
I'm with you. Other points. Go ahead, Keith.
I know I'm going to somewhat disagree with your market and technology thing. I know you said just consider technology, but the other thing is, it's one thing to say, yes, we have a vehicle out there that can reduce it by 80%, but again, you look at a fleet, I forget the last time I saw what the vehicle fleet is in the U.S., but it's like, 200-some million or something. And so you're going to say, sure, a vehicle that in the average vehicle life is somewhere in 10 to 12 years, I think, and it's
Maybe
getting
longer.
bigger. What's that?
Maybe longer.
Exactly, I think it's getting longer. The trend is shown. So when you say 2050, it's possible the vehicle life 15 years or more. So actually, to replace the entire fleet, we would have to implement that 80% reduction by 2035, not 2050. Or we're just going to tell everyone, I know you have a perfectly good vehicle, but get rid of it and buy this newer one. So
that'd be great for the economy, right? Well, we'll just put it on our credit cards, right? Thank you. That's a good point. Let's talk about the market side, because I think most people think the technology is there, but I think where everybody's going, or a lot of people are going, is on the market side. So how many people think it will happen? Oh, really? That's depressing. We got one. A couple of optimists. Either of you willing to share your optimism? Bring some sunlight into the room here. Go ahead.
Happen because, like we discussed, we do have the technology, but it has to happen with a shift in the people who want to keep the power. Like, there are huge corporations that make all their money out of people driving cars which run on gas. So once we have that shift, and most importantly I feel is we have the support infrastructure, like cars are becoming electric, like from conventional to hybrid to eventually electric. So once we have the infrastructure figured out, as in charging stations like what Norway is doing or something, we'd get that. Or we have a system where we swap batteries, like if you go to a gas station you have a battery swapping system or something. So once we have that in place, I feel it's definitely doable by 2020.
Anybody agree or have a counterpoint?
I think the issue partly is psychology. It's that people don't want to be told that they can't do this, or they aren't allowed to do that or own this or that. You know, they feel like they have the freedom to choose whatever they want, and so I don't know. I think part of it comes down to yourself.
This kind of reminds me of the incandescent light bulb story. All right, has anybody been following that? Anybody willing to share? What's going on with light bulbs? Good.
Essentially, they're phasing out the conventional incandescent light bulb, and people are forced. There's going to be a switch over to CFLs, which is going to be required, so people are actually stockpiling the incandescent light bulbs because they like the way it looks, they like the softer light, and they really don't care about the energy gains that you get from the CFLs.
And some folks trying to reverse the law. Haven't been successful yet, but you never know. So that's light bulbs. They're not so expensive. So you know, in the scheme of things, right? So you know, that's why your comment, Monica, kind of reminded me of that. You know, so but not to be too pessimistic. So what's the pathway forward? If we, let's say, okay, we're not going to get to 80%. Let's put a big dent in this thing. You're all in charge. What would you do? Go ahead.
I mean, I think you have to take the government route. You can't rely on the market demands to filter up through corporations and then through the corporations to produce the right, you know, combination of vehicle or change electrical or change the power sources. So I think it's got to be government intervention to get it done quickly enough for that date. And so, I mean, you got to elect different officials and that sort of thing.
Go ahead.
Maybe I'm just being pessimistic too, but on government regulation, I think from what I've heard about what regulations have to be enacted, I don't think that it can happen in the time period that we have for 2050. Maybe I'm pessimistic about the time that government takes to really make these regulations.
I mean, they've already
and
proposed
enforce them.
55 miles per gallon for 2025. So, you know, that's putting a big dent in it.
You have a car and it's old, but you're gonna need to get a new one. I don't think that the time frame.
But you're already talking, you know, 2025. You're going to be up at 55 miles per gallon. Those cars will be off the road by 2050, right? So there's opportunity to increase it still further. Go ahead.
It's also whether or not the companies can afford these kind of regulations. It's easy to say, you know, you have to make a fleet of these cars and they have to have certain mile per gallon, but in the end, if the companies can't afford that and they end up going under again or something, people lose their jobs, that you have to look at that side too. So
Sure. You know, where do the companies get their money from? It's an obvious question. People buying cars, right? So at the end, this is about the people, right? So companies will do what the people want. And that's why, you know, when you talk to people about what's going on in materials, so I've got some friends at the big three, and you talk to them and say, well, this is something we can control, right? But those consumers, we can't control them. We just give them what they want. And there's some truth to that, you know, and I'm not saying that, you know, some of the companies have not pushed big cars onto people who might not have otherwise gotten them. But, you know, we did an interesting thing, PhD graduate a few years back. We took a demand model from basically using data from 1990, and we put the cars from 2005 into that model, and we just wanted to know if it would predict the prices of 2005 cars, like basically the willingness to pay that people have. And it nailed it. In other words, there was something inherent to the consumers there that was constant over that 15 years. And what that says is, there are a lot of people are mentioning values here that that's the time constant that maybe is a bigger concern. Because if the hearts change, then the wallets would change, the wallets would change, and the companies would be all right. But yeah, you can't have those two things out of sync, right? Clearly. And then the companies, there's so much money involved with rolling out a new car that obviously they're going to be conservative about it. Go ahead, Pete.
Yeah, and I think a lot of the times politics, like all these companies are supporting the politicians behind all these decision-making power, right? And if they don't see the consumers asking for them to do something, they're gonna put the money into lobbying to keeping the same old regulations or whatever they have in place right now. And so I think really the big question is behavior change, and can we get that? And I think that has to start from education. And and what I'm not seeing now is really that sort of like interdisciplinary, multidisciplinary piece of education where you get the policy people, the econ people, and the technology people together, right? And programs like Interpro is doing this, but I'm doubtful that this movement is going to happen fast enough for us to meet this target.
So Pete's got the last word here, and I want to just sort of add to that by saying largely engineers are not involved. Engineers, as I look at this discussion we're having and the discussions that are happening nationally, I think engineers are in a great spot to understand all these issues. They can't work alone. You need to have the people in the room, but in terms of being able to grasp all the issues and the decision making among trade-offs, that's an engineering skill, but the engineers are largely absent. So, I think that is part of the culture change here. I'd like to see more of folks like you in those kinds of discussions moving forward. I think it's just going to be necessary. These issues are complex, right?